Hello again. The last time we left this, I went over this proposed protocol that I'm going to use to implement the control of a CAN bus network. And it's basically transmitted over an 11-bit standard identifier. So standard frames, we're looking for standard frames. Now the network can also transmit extended frames, the 29-bit identifier, but this protocol is only transmitted over the 11-bit. The top 2 bits priority. The next bit is a request, a remote transmit request. That's a typo. So next bit, 2 priority bits, a remote transmit request bit, and then the remaining 8 bits is 1 byte of the identifier, which specifies the type of payload that's been carried by the frame. So we specified last time, it specifies the type of frame and the encoding of the address of that payload. So we specified 2 Booleans last time. I called them switch inputs and outputs, but they're really Boolean in programming terms, Boolean output, Boolean input. And they're encoded in 431. So of a possible 16 nodes, 8 outputs per node of an output, and the same for an input. Now, we speculated on other possible frames, so we could have a Boolean value which is actually transmitted in a 16-bit data payload, in which case we could potentially have 8 bits of an address, 7 bits of a channel identifier, and then the actual Boolean value. So back to an implementation, I should actually point out in the electronicSoup on GitHub there is the libeSoup repository, but there's also ESCAN node, which I haven't dealt with yet, but this is the start of looking at an ESCAN node, and that's what all these 4 nodes, cinnamon buns, are going to run. Now the ESCAN node is it's kind of like an operating system. It's taking care of all the underlying activity on the actual cinnamon buns, and the application is built on top in a similar way to the Arduino, which has a setup function which is called an initialization and a loop function which is called periodically. In this architecture, the names have been changed. We've got an application init function, which, as the name suggests, is called an initialization, and then app main, which is called regularly, at regular intervals. So, and this is all built on top of this CAN node. Now I've got a couple of different configurations, is what they're called in MPLabX. I've got a couple of different configurations on this project. This is not the way it's going to be done ultimately, but for the minute this is the easy way to do it, is to actually link everything in together in one big executable. So we're bundling up the CAN node kind of operating system and the application on top. We're building everything, and you'll see that if I actually build. I've got the controller configuration selected at the minute, but you can see the amount of files that are getting built there. There's quite a lot of code getting all bundled in together, whereas this application for the output node, so we've got 2 output nodes that are just running simple LEDs. That application is this one small file, and an initialization, all this node is doing is initializing its outputs. It's initializing all 8 pins, RD0 to RD7, to be digital outputs, and initializing them to 0. And then it's creating it's registering 2 handlers for frames, CAN bus frames. One is on the 431 output, the Boolean output 431, with the RTR bit set. And in that case, we're going to call this switch output RTR handler. We're doing exactly the same thing again, only this time we're only setting it for the 431 output. We don't care about the RTR. We want it to be no RTR. If it's not an RTR, we're just going to process this normal and call the switch output status. And again, we register that handler. So all this does is register 2 handlers. Now there was some other code for test purposes, which is in that. I mean, this is all, can is always defined in this. This was, I should actually get rid of those. And shorten it even more. So I was using timers for this output node, but that's the output node there. A simple initialization set up 2 handlers for 2 specific frames, and when that frame is, that's the RTR handler, when we get a change in status, we loop through the data bytes. We know what the configuration is. It's a 431 node address, output channel and Boolean value, and one of the parameters to the initialization is this node's address, so we know what node address we're handling. So we loop through each of the bytes, and if the byte is for our node address, we just set the GPIO of that channel to whatever we've been passed. So if we get a frame with a data byte that says turn channel 1 on or turn channel 1 off, we just do that. And that's all this node does. So this is purely an event-driven piece of code. The actual application that's periodically called, the function which is periodically called appmain, does nothing. It just returns success. So this is purely event-driven, and when we get the frame, the events in this case are specific CAN frames. We just want to process those frames. In a similar way, the input node, it's a different configuration here, but when that is initialized, I better change that back to the controller because I'll forget I've changed the configuration. When the input node is initialized, we set up, this time we're setting up on the 431 input. We're only interested in input, Boolean inputs, 431 encoding. And this is a frame that's for the remote transmit request, and if somebody sends us a request for information about our inputs, then we want to process that using this switch input RTR function. Otherwise, the initializer just sets up an actual frame to transmit by setting the identifier to a really low priority, the lowest priority possible, sets the CAN identifier to the actual 431 input, which I've controlled all that information in that document with these encodings. I've put into escontrol.h. So our Boolean 431 output is a hex value of 10, and our input is a hex value of 11. So our input node sends a Boolean 431 input frame with its inputs. So it loops through its inputs. Now this code I've set hash defined, I've set this number of inputs to 4, even though I've only soldered 2 switches onto a board. It doesn't really matter. This is going to send 4 inputs that are off, or send 2 inputs that are always going to be off during initialization. So this is just sending initialization, so that when the network powers up, this input node will send the status of its 2 switches. Now I've reversed the Boolean because my node actually has pull-up resistors. So when the switch is pressed, then it will go high, or sorry, go low. So I've reversed that in the logic of the code. So when we press the switch, we send a high value or a logical Boolean true, even though the voltage has gone low. So it's just reversing the logic. So put together that frame of all our inputs and transmit it. So anybody interested in what our status is. And then their application main, in this case the application main actually does something, and it basically loops around checking its inputs and seeing if they changed. And it debounces those given parameters defined in the top of the file and puts together a frame. I mean, it starts out with setting up a low priority 431 Boolean 431 input message or frame, sorry. Sets up the identifier, sets the data count to 0, and only if one of those, only after debouncing the switches and a change of state do we add a byte encoded in a 431 specification. We configure that byte, or we set that byte, and then we load it into the frame's data, the payload of a frame. And we pop out of this function, we just say, if there's any data in the payload, send that frame. Otherwise, don't bother. We can ignore it. So most of the time, this input node is just going to go loop around, checking inputs, but nothing's changed. And those two types of node, the input and output, if we disconnect the controller, as I call it, this is waiting for 431 output frames. This is transmitting 431 input frames. So when it transmits those frames, nothing's going to happen. So all the logic is built into this controller node. And what the controller node does, it's got a very simple application as well. It's only interested in 431 inputs. So again, it's an purely event driven, because the main loop does nothing. Purely event driven, and the only events it's interested in is 431 input frames, Boolean 431 inputs. And if they occur, the underlying CAN node, operating system if you like, is going to call this callback, process the 431 input. And the 431 input function, all it's going to do is loop through the payload. There's a possible 8 bytes of payload in this frame, but it's only going to loop through what's been received. And if the byte has come from node 1, input node 1, then we're going to call node 1 431 input. All that function does is work out which switch it is. So if it's the first switch on D0, call node 1 channel 0. Otherwise, if it's the second switch on pin D1, call the other function. And all these functions do, these are quite long logically, because all they do, if the frame is set, so this is the first channel 0, and it's going to loop all through all 8 outputs of the output frame of node 1. So 431 output, node 1, set the Boolean to true, and put a byte together for all 8 outputs. Load up the frame and transmit. Similarly, if we get a status of a Boolean value of false, then we load up 8 data bytes and set all outputs on node 1 to off. And we do exactly the same thing on the second switch, but we do it for node 2. So if we look at a network, now that we've got the master plugged in, if we hit the first switch on pin D0 it sends a 431 output message with 8 bytes, all addressed to node 1, output node 1. So all 8 outputs light up. If I hadn't run out of resistors for node 2, then it would do the same, but we've only got 4 outputs. But you can see what's happened. And now the beauty of this is that this is all contained in the controller's logic. So if we want to say, when switch 1 goes, instead of doing addressing all our 8 bytes of payload to node 1, let's say if the loop is less than 4, there's only 4 outputs on node 2, so if loop is less than 4, node will address to node 2. If it's greater than 4, address it to node 1. So in this case, we should set 4 outputs on node 1, 4 outputs on node 2. So we've changed the logic, and hopefully, so we've changed the switch's logic. Now whenever it's pressed, we've got 4 outputs node 1, 4 outputs on node 2. The old switch still does what it did. Now, what happens if we actually want to send more? So we could actually send all, assuming that we had 2 output nodes with 8 outputs each. We could repeat this block of code and say, so in this case we're going to load up our frame, and when the frame is full, we're just going to transmit it. But we can keep loading it up. In this case, because we're doing this, loading it up twice for every iteration of this loop, we're going to send 16 data bytes as payload. So we have to split it between 2 frames. So we should do exactly the same when we're switching it off. We want to switch off all 8 outputs on node 1. And all 8 outputs on node 2. So this is going to be blindingly bright. If it works. So that's actually sending 2 distinct frames. And because of the way we wrote the code, it's going to light. The first frame is going to turn on output 1, 1, 2, 2, 3, 3, and 4, 4. Or 0 to 3 if you want to count from 0 up. But those first 4 and those first 4 in the first frame, and then the master is going to send that frame on the network and then send the next frame with the remaining outputs. But it's going to happen so fast. CAN bus is working at, I think I set it to 250 kilobits per second. So it's going to go much quicker than you can actually see it, unless the actual network, the CAN bus network, was busy with other stuff. But this is a very small network with only 4 nodes, and we're sending out those inputs. And that's pretty much it. This is the advantage of this proposed protocol, is that you just change. These are fixed. These don't have to change. Like this output node is a very simple task. Turn on and off 8 outputs. this output node is exactly the same functionality, the same code. It's working on a different address. Now how it gets that address we'll have to come to in a different video, because at the minute I've hard coded them. This input node knows exactly what it has to do, and it just monitors switches. And if a switch changes, sends a frame. So all the logic is built into this controller, and we change that logic, edit that logic to how we like. Now obviously I'm doing this in C code at the minute. I'd much prefer to spend the time and do something graphical, but that's down the line. I mentioned the way that GNU Radio works is with dragging and dropping blocks of functionality. That would be brilliant. Might get to it eventually. But that's the actual practical implementation of this very sketchy protocol at the minute, because I've only done switching things on and off. I'll leave it there for now. Thanks a million for watching.